Very good afternoon. I welcome you all to the 2944th lecture of prestigious Bangalore Science Forum. A hearty welcome to the guest speaker today, Dr. S. Raghunath. And I also welcome the Vice Principal, Srimati Alkananda. A hearty welcome to all the faculty of National College present here today. And once again, hearty welcome to all of you. Firstly, I'm proud to share that Bangalore Science Forum, which was founded by legendary Dr.HN in 1962, has been honored with Kempegowda International Award recently. So now let me take the privilege of introducing our guest speaker. Dr. S. Raghunath, a retired professor of civil engineering, has had a distinguished academic tenure of 36 years at BMS College of Engineering, Bangalore. He holds a BE in Civil Engineering and an ME in Construction Technology from UVCE, Bangalore, and a PhD in Structural Engineering from the Indian Institute of Science, Bangalore. In Bangalore, where he was mentored by Professor K.S. Jagdish. His research interests span structural masonry, experimental dynamics, earthquake-resistant buildings, alternative building materials and methods, energy and buildings, and the restoration and structural strengthening of heritage buildings. Throughout his career, he supervised 10 doctoral research projects and over 60 postgraduate dissertations, conducted several sponsored R&D projects, and published approximately 60 research papers. In addition to his academic achievements, he served as a structural consultant for numerous governmental and private agencies, particularly in the areas of structural masonry and heritage building restoration. He is also actively involved with Nivasa, an architectural NGO dedicated to enabling humane and dignified housing conditions for the urban and rural poor through innovation design. I welcome Dr. S. Raghunath once again on behalf of Bangalore Science Forum. Over to you, sir.
Good afternoon to all of you. Namaskara. First of all, I would like to thank Madam Sucharita for inviting me. And before that, I would also like to thank my former colleague, Dr. Varsha, for setting up this lecture. I remember quite a few years back, maybe about 4 or 5 years back, that I was telling her about the fact that I used to attend several lectures in this August forum. God knows how many lectures I have attended here during my high school days and college days. I always looked forward to listening to the lectures here from so many people. And I was telling her that it was a dream for me to deliver a lecture here. Okay. Thanks, Varsha, for doing this. I will start off with a small disclaimer in the sense that this earthquake engineering is a very broad topic. Indeed, as of now, earthquake engineering itself is a complete postgraduate program. It's spanning over 2 or 4 semesters, 2 years. There are a whole lot of courses in earthquake engineering, like structural dynamics, finite element analysis, design of earthquake-resistant structures, disaster management, and modeling of the seismic forces, and then predicting, and then things like that. A whole lot of things, geotechnical earthquake engineering, things like that are there. To present an overview in this next 50 minutes or so is quite formidable. I don't know how I'm going to make use of this opportunity to make it eclectic to this audience. Okay, let me see how it goes. That is one disclaimer I will start with. It won't be very technical. Okay, so I thought I will deliver this in 4 parts. I'll come to that very soon. Secondly, The insights for earthquake engineering for me came because of several associations with many people. My own Professor K.S. Jagdish, he was my mentor, and he was the one who introduced me to this subject. Okay, I got a lot of insights into this, and then of course my interaction with my friend Vijendra, who is an alumni of this institution, and then my teachers at Indian Institute of Science, and a whole lot of other professionals who are associated over the period of my tenure at BMS College of Engineering. I was able to read through a whole lot of books, and then I was always fascinated about this topic. So I duly acknowledge all these things. Okay, so there we go. So I would like to acknowledge, and of course, my former students, colleagues, and professional associates. Okay. So most of the illustrations and in this presentation are taken from different sources. Wherever possible, I have given the sources. Okay, so the structure of the presentation for the next 50 minutes or so will be sort of 4.5 parts. It's not exactly 4 parts. In the first part, I'm going to take you through some images of buildings and infrastructure which have suffered because of earthquakes. And then in the second part, I'm going to talk about the brief introduction to seismology. Why do things happen like that is what I'm going to talk about in the second very brief part. The third part, I'm going to talk about the science behind seismic design philosophy. Of course, like any other science, this is also an evolving science. Okay, so I'm going to talk about that in a little bit. There could be some technical content in the third part. And the last part is, of course, once you understand the science and the philosophy behind earthquake resistant design, you need to convert that into technology. After converting that into technology, it has to get disseminated and become useful for the society. I'm going to talk about that in the last part with some closing remarks. So here we go with some images of earthquake damage. I have collected some images from very old earthquakes. I mean, in the sense that some literatures which are well documented. Oldham was a pioneer in studying this, one of the classical earthquakes which happened in the earlier Indian subcontinent. The 1897 earthquake was completely documented by Oldham, Richard Dixon Oldham, and his several of his treatises and books and then articles. Here is a picture of a school building, which was, fortunately, both the pictures were available before the earthquake, and of course, after the earthquake, it had become rumbles. Okay, there's absolutely no sign of any usage at all. Okay, it is completely devastated. Okay, we call that as grade 5 damage. Okay, you can see the building in the foreground as well as the beautiful bungalow type of building in the background. Both of them collapsed in a few minutes, quite literally few seconds. In fact, so devastating was this earthquake that it was called as a Great Indian Earthquake of 1897. At that point of time, this was supposed to be one of the biggest earthquakes. Even today, it comes into the top 5 biggest earthquakes ever. And then he has also recorded quite a few things, and if you read the reprints of his diaries, you find some very interesting and devastating photos of railway bridges completely distorted. Okay, and you also see one masonry building completely damaged on the right side. Few more pictures. Okay, the one on the left-hand side is a church. It's the All Saints Church in Assam. It was a well-known church. We have an All Saints Church in Bangalore as well. And then there was this collector's office, district collector's office. And you can see a beautiful building coming down to the ground. So these were all recorded during that earthquake. Of course, when buildings collapse, they also cause fatalities. Okay, so this is something which civil engineers should not be doing. I mean, civil engineers should take this as a challenge and then see that these things do not happen. Okay. So now the interesting story comes here. a series of articles written by Oldham and then later by Bilham and quite a lot of others, Britishers, they documented this. And unfortunately, in the year 1931, there was an earthquake in Bihar and quite a lot of regions in Pakistan, and of course, in some regions in the foothills of Himalayas. A lot of buildings did collapse during the 1931 earthquakes. They are called as the 1930s sequence of earthquakes. During that time, there was this railway engineers started by Britishers. One enterprising engineer by name S.L. Kumar, he took it upon himself, he and his team, why don't we construct earthquake-resistant buildings? At that point, they called it as earthquake-proof buildings. They did a whole lot of studies and then tried to understand how buildings behave during earthquakes, and then they tried to understand the materials, they tried to understand the configuration and things like that. And then they came out with a very interesting, in fact, I'm going to leave this presentation here. You can go through this. There are about 20 pages of calculations and the engineering behind that, the science and engineering behind this. Even now we follow the same thing. So his article was titled as Theory of Earthquake-Resistant Design with a note on earthquake-resistant construction. Okay. What happened was very interesting. Quite a few new buildings were constructed with this technology developed by Kumar and his team. And in the year 1934, 31 and 34, there are again quite a few earthquakes. The buildings constructed with this technology survived the earthquakes. The buildings which were not constructed with this technology was completely devastated. So in a way, this period is the benchmark period where the understanding and behavior of buildings during earthquake was consolidated, and then the technology came. Okay, so they had the understanding of buildings during earthquake. I'm talking about generally, in particular in India, and then the technology was the output. Okay, this was an amazing lesson which Indians learned. Okay, but unfortunately, this did not translate. You know, India is a vast country. Okay, what happens sporadically could not be translated. Okay, so we quickly come to 1993, almost 100 years later. Of course, after the 1930s earthquake, 60 to 70 years later, there was this earthquake in Killari, the village of Killari in Maharashtra. The entire village just came down to rubbles. Quite a few people died, thousands of people died. Okay, so the entire village, Killari village, came into rumbles. Okay, so they did not have absolutely any clue that there was something called as earthquake-resistant design. This led to one very interesting thing, that masonry buildings are unsafe during earthquakes. Okay, so at that point in time, the engineering fraternity thought that masonry buildings are the ones which are very, very vulnerable to earthquakes. Of course they are, okay, but it took a very bad name. So that is 1993, September 30th earthquake. We move on to the next major earthquake in India. In a way, this is also another benchmark earthquake. The Republic Day earthquake of 2001 in Gujarat. Some statistics, nearing 170,000 people were injured. A lot of people died. Okay, so people say that almost 90,000 people died. Officially, it was recorded as 14,900 people who lost their lives during that particular event. Later, within a span of another 1 week to 15 days, a whole lot of people died. So probably nearing 90,000 people died. What was unfortunate was one of the first building to collapse was the Bhuj hospital. There are 2 hospitals in Bhuj. Okay, both of them collapsed. Okay, and the inmates also died during this. I remember myself and Vijendra, we had been to this place in the month of March, 2 months later after the earthquake happened. And this was completely devastated. Okay? And we also remember the people telling that after the earthquake, the people in the surrounding districts and villages, they traveled to Bhuj wanting their injured to be treated. Okay? When they came here, they found the hospital itself had collapsed. Okay? Quite a lot of medical personnel, medicos also had lost their lives. This was an unfortunate thing. And adding to the misery was a lot of so-called modern structures also collapsed all over Gujarat. Okay, Okay, the kind of buildings which you say, fantastic building. These kind of buildings you see even in Bangalore, contemporary buildings in Bangalore, they collapsed. Okay, and these are the typical RCC buildings, they also collapsed. It's not that only masonry buildings collapsed. At this point of time, there was a furor in engineering that, okay, look, RCC buildings are also as vulnerable as masonry buildings. Okay, so in a way, this was also a triggering point. There's something interesting which happened. I'm going to come to that very soon. And it was and quite a few buildings which had not completely devastated. It had distorted so much that search and rescue operations were also almost impossible. Many people lost their lives because people could not go inside the building and then retrieve the bodies. So we did not have technology to do that also. Okay, unlike in Western countries, they have a lot of technology. So this was quite devastating. They had to improvise a lot. Okay, and then some makeshift arrangement had to be done. Remember, this has happened over almost the entire state of Gujarat was affected. In a way, our nation was affected. Okay. So these were some of the preliminary pictures of 1 or 2 days and 1 week later. And even I remember when we went in the month of March, even then debris were being recovered and some bodies were being retrieved and things like that. Okay, so this is what happened. Generally, it was a problem for all sections of the population, particularly women and children. Okay, so for a long period, they had to live in makeshift tents and things like that. It was very difficult. Okay. So despite this, the beautiful thing about this thing is, despite this, lot of surgical interventions were done in the makeshift arrangement. Entire India responded to that earthquake. Okay, socially there was a huge amount of awareness among common people that look, this is not a disaster which has to be taken lightly. Okay, it has to be taken on a national scale. That was when the Ministry of Housing and then Home Ministry took it upon themselves to come out with a major program called as the National Program for Earthquake Engineering and Education. So that was a turning point in our earthquake engineering history. And a lot of students were sensitized about this. And that is on one part, on the systemic level, and at a policy level it happened. At the ground, something else happened. A lot of local engineers and architects, they started responding to the way the people understood about the buildings. A lot of architects and engineers, they came out with their own way, innovative way of understanding what has to be done and what should not be done. Okay, a whole lot of NGOs started. And of course, Varun is here. Hunar Shala was one of the premier organizations. Kutch Mahila Vikas Sangathan, CDAP and NCPDP and Center for, people in Center, whole lot of NGOs in Gujarat. They started understanding earthquakes and then earthquake resistant design and construction, and then started training all the local masons and then contractors and engineers there. Okay, much before the government could do it on a systematic scale. Okay, so two things beautifully happened. Okay, organically NGOs started working, and the government also initiated a series of programs. Okay, this is when we went in the month of March, we saw this building collapse. Actually, you can see it is turned by 90 degrees. It was completely fell down. In fact, I remember that this building fell on the neighboring building, and the 6 people in the neighboring building died. And the people inside this building were rescued by puncturing holes in the you see this fan, it's not a wall fan, it's a ceiling fan actually. Okay, this was the amount of devastation. Okay, a very modernistic building, RCC building, it has collapsed. Okay, used to be a 5-storied building. The columns completely crushed, and then it came down to rumbles. This is one building, a 2-storied building, typical, you see a beautiful 2-storied building even in Bangalore. It was yet to be occupied. While we were traveling from Ahmedabad to Bhuj and then from later there to Khavda, we saw this in a village near Samkyali. It was a building from far, we saw this and then we wanted to see, and then we saw new building. Okay, so though the building had not collapsed, okay, a lot of damage had happened. Okay, so this building was waiting for the housewarming to be done. It was a very sad thing. Okay, On one hand, people had lost their lives. Okay? On the other hand, the loss of property. Okay? In many ways, it was a double whammy for the state of Gujarat. Okay? And so people were there in Gujarat. I mean, I know Varun's teammate and Dr. Yogananda was there in Khavda. A lot of masonry buildings also collapsed. Okay, so some of the pictures I have taken it from them. Okay, these are some of the pictures I got it from a couple of friends from Nepal and New Zealand. Very interestingly, it's not that earthquakes are going to affect only the developing countries. Even developed countries have been affected. Okay, this is one in one of the developed countries. This is the one picture shared by Dr. Jitendra Botara from New Zealand. Canterbury earthquake caused a lot of devastation, okay? And then railway lanes distorted, okay? You can see the amount of the ground movement in these pictures, okay? And you can see the highway, okay? So it's distorted. So this was the building in Canterbury. And again, just like it happened in India in the 1930s, during 2010 to 11, there were a series of earthquakes, moderate earthquakes, not major earthquakes in New Zealand. So a lot of buildings collapsed. And then many people migrated from Christchurch to Wellington and other places. So they came out with a different type of solution for earthquake-resistant construction and then policies. I'll come to that also later. This is another example of how infrastructure, okay, is going to be devastated. This is the earthquake which happened in Japan. I don't remember this. Okay, I think Fukushima earthquake. Oh, Kobe earthquake, yeah. And you can see the piers of a flyover, okay, crushed beyond redemption. Okay, we want to test a small specimen in our laboratory. We need so much of energy to crush it. Here, a series of piers, okay, got crushed beyond recognition, okay. And then there is this, of course, this is in the Canterbury earthquake, okay. And people were seeing their buildings and then vehicles. They went inside because of a phenomena called as liquefaction during earthquake. And this is one of the, again, Chichi earthquake. There was this damage of a dam, water retaining structure. This is the Niigata, 1964 Niigata earthquake. This is a cover page in the book written by Kramer. All the buildings are intact, but the soil beneath the building converted itself into a sort of a liquid kind of thing. So it behaved like a liquid, and it tilted. It did not have any pressure or bearing capacity at all to withstand the load of this building. So it simply tilted and fell down. Okay. So these are the few pictures. And then lastly, I'll come to this fatalities, okay? During the first half of the 20th century, nearing 8 lakh people died. And many of them died because of collapse of masonry buildings, nearing 70% of the people, okay? And during the second half, between 1950s to 1999, 7 lakh people died, okay? And again, the share of people who died because of collapse of masonry buildings has not come down significantly. And the number of people who died because of collapse of RC buildings, because RC was not common during that day. And unfortunately, after 2000 till 2023, the number has doubled actually. Okay, so that brings us to one very uncomfortable situation, especially for engineers. Have we learned something or have we not learned something? The answer is yes and no. Okay. If we have learned something, okay, then the fatality should have come down. Okay, so where does the answer lie? Okay, that's something which we need to ponder. I'll come to that during the last part of my lecture. So this was about the. I was trying to sensitize you people about how earthquakes are very devastating. Okay, and sitting in a place like Bangalore, we have not even felt a tremor, okay? Apart from traffic jams and then garbage and then water logging and things like that, we don't find any problems in Bangalore as such, okay? So just imagine you're walking in a street and all the buildings have collapsed, okay? it's unimaginable, okay? The kind of psychological damage it causes, okay? And one people died in your street, it causes some distress. And several people died in the street, it is something which is unimaginable, okay? I also remember when me and Vijendra and my professor, and when we went there, when we saw the pictures, it was one level of understanding of how buildings behave during earthquakes. When we went there, it was a totally different thing, okay? And for people who have experienced those earthquakes, it was really, it's a huge psychological distress, okay? Whoever survived those earthquakes, they would have undergone a huge amount of agony, okay? So, the answer that, okay, should we learn something about earthquake engineering? The answer is emphatic yes. There's no two ways about it, okay? You have to learn, you have to understand, you have to move forward, okay? You have to disseminate the technology, okay? So, with this as the background about having understood that, okay, earthquakes are a problem for humanity in general, okay? With this as a background, I'll come to the second part of my lecture. What causes these earthquakes? Okay. Broadly, earthquake means in bhukampa, the ground shakes. That's the broad understanding of earthquake, okay? So I will go on, I'll devote a few slides, maybe about 5 to 6 slides of what causes an earthquake. And this is something which is, again, evolving science, okay? Very interestingly, I think many people know about this, okay? If you look at the structure of our Earth, planet Earth, okay, typically in terms of the geology, you can classify that as the crust where the thick rigid mass is there. Crust consists of both land mass and oceanic mass. Beneath this crust is the 3,000 kilometer thick mantle, and beneath that mantle is the core. Of course, the core is divided into outer core and inner core, okay? So, this is how it is, and I think all of you know that the inner core is, the temperature is very, very high, okay? There's a huge temperature gradient, thousands of degrees of centigrade, okay? And then because of the fact that Earth is moving and revolving and things like that, okay? The surface of the Earth, the crust, okay, is, though it is solid, there are a lot of fissures, like the cream on milk, hal mel kene kattatala atara, it's like that, quite literally that, okay? In terms of scale also, it's just, we are living on the thin cream of this crust, okay? It keeps moving relative to each other, okay? And very interestingly, a lot of seismologists, they tried to track these earthquakes, and they found a very interesting pattern, okay? One Wegener was supposed to have told that, okay, look, these are the tectonic plates. Each dot represents one major earthquake event, okay? And there are a lot of, this is the African plate, this is the Indian plate, subcontinent plate, and Russian plate, okay? Atlantic plate, Pacific plate, North American plate. They are moving against each other relatively, okay? So this was one of the hypotheses propounded by a lot of people, and then there are a lot of evidences to show that this hypothesis is quite true, okay? So the major two reasons why earthquakes happen is because of volcanic activities. The other one is tectonic activities, okay? This is the one which is most devastating in the sense that volcanic activities, you know which are the active volcanoes, which are passive, which can become active and things like that. And you can actually have the civilization away from that. But these are the places, and if you look at the entire thing is, civilization is around there. You can't move away civilization there, okay? And you look at this cap of India, the Indian subcontinent, and then the entire thing here, okay? So, and Europe, quite except Britishers, okay, who colonized us and did not train us on earthquake engineering, okay? So, so this was the one which was propounded by Wegener, okay, and it's an accepted hypothesis, okay? It's an evolving science, okay? So, a lot of evidences, okay? In a schematic diagram, two tectonic plates pushing against each other, okay? It could be in the form of compression or shear or twisting, okay, or tension, okay? So they move against each other. Huge amount of strains are accumulated, okay? Huge amount of strain energy is accumulated. At one point, suddenly it snaps, okay? That huge amount of energy which is accumulated releases, okay? And releases several kilometers beneath the surface of the Earth, okay? Where the first point where the energy is released is, of course, it's called as a focus of the earthquake, And the point where the projection of the focus onto the surface is called the epicenter. Okay. Now, the thing is, there's a huge amount of energy which is released. Okay. Normally, when energy is released, it will get converted into other forms of energy, or it has to dissipate. Okay. Unfortunately, in this case, because the first source of energy is deep beneath the surface of the earth, okay, it has to get transmitted through seismic waves. Okay. So how it is going to get transmitted is very interesting. So there will be waves which are going to, it's just like dropping a rigid object on a still surface of water. When you drop that, the kinetic energy of the stone which you are going to drop on water is converted into, the potential energy is converted into kinetic energy, and then once it hits the surface of the water, the energy has to be dissipated into other forms. It creates ripples. Okay, exactly same thing happens here. Okay, exactly. The strain energy is converted into some other form of energy, and it has to get transmitted in the form of waves. Okay, it can't get transmitted in the form of light and sound waves. Of course, sound also emanates. Okay, but mainly it has to be in the form of seismic waves. Okay, there will be what is called as compression waves. Okay, a small animation to show that how the waves travel through the surface of the crustal layers, and these are the shear waves. Okay. And once it comes to the surface, there will be what is called as a Rayleigh wave, and then there is this, what is called sort of the twisting type of motion called love waves. Okay? So this is what happens on the surface of the earth. The buildings and the infrastructure is constructed on top of the crust, okay, has to endure all these things. Civil engineers are fantastic in designing structures for all types of loads which are static in nature. Dead load, live load, and nearly static in nature. We can also design structures for wind loads, settlement loads, fire loads. Talk about any loads, we are very good in designing structures for that. Okay, we know how to make a structure rigid and strong, stable for all configuration, all categories, and for all combinations of load. But unfortunately, earthquakes cause what is called as a dynamic load on the structure. This is a challenge for civil engineers. Okay. A small digression away from this. In fact, understanding of the structure of the earth has happened because of earthquakes. We would not be knowing that that is the structure of the earth had there not been any earthquakes at all. Okay. An exciting phenomena. Okay, and of course for civil engineers it's a dreadful thing. Okay, so we use earthquakes to locate the earthquake. We use earthquake to find out the structure of the earth, things like that. Okay. So this is about this. Okay. So to sum it up, this huge amount of energy is going to be transmitted in the form of seismic waves. These waves are going to cause ground vibrations. You saw the ground vibrating. I mean, the pictures of the ground distorted. Okay. The buildings and structures which are situated on the ground are going to shake. Okay. How are you going to handle those ground shaking? Is what we need to understand in the next part. Okay. Of course, again a little bit of digression in terms of understanding the size of the earthquake. Okay, there are two scales. One is called as the intensity scale. What is the amount of energy which is released during an earthquake? Okay, that's called as the magnitude of the earthquake. How much of damage it has caused to the infrastructure, to the people? Okay, it's called as the intensity scale. Okay, of course, intensity scale is qualitative. Depends on how badly the infrastructure is there, how proximal the infrastructure is there to the epicenter, okay, and how far away it is there, okay, things like that. Whereas magnitude scale is very popularly used by geologists and seismologists to tell the amount of energy. So bigger the magnitude of the earthquake, large is the amount of energy. Okay, so there is no doubt about it. Okay, but for civil engineers, both of them are not of significance, unfortunately. Okay, okay, by the way, one more slide, just to tell that earthquakes are actually not a very uncommon phenomena. If you look at this graph, okay, so magnitude 2 earthquake, there are more than 1 lakh of earthquakes which happen every year. Okay, in fact, as we speak, there will be some earthquake somewhere or the other. In Japan, there'll be a magnitude 2 or 3 earthquake almost every week. Okay. In fact, in Assam also, okay, once in a month there'll be magnitude 2 or 3 earthquakes almost every month. Okay. It's not very uncommon. Okay. But of course, as you know, that it's a logarithmic scale. As you go up on the magnitude scale, the amount of energy released is phenomenal. Okay. There's a kind of earthquake. Just marked it here, Gujarat earthquake. Okay. It is something here. Okay. The Chile earthquake is there. Alaska earthquake. Okay. So this is 6.8 magnitude earthquake, and you know what's the amount of damage it caused. Okay. So that's there. Okay. So moderate earthquakes are not so very common. Major earthquakes are even less common. Okay. It is the moderate earthquake and the major earthquake which we need to keep a track of. Okay. Okay. So that understanding of science, where earthquake happen, what is the size of the earthquakes, okay, which are the places which are more prone to earthquakes and things like that, has helped our engineers. And one very interesting thing, if you look at the map of India, these are the places where earthquakes have happened. Okay, automatically the seismic zoning map of India comes. Okay, so it's very easy. One of the first lessons which you have learned, or by intuitively you can say that, okay, don't construct buildings in zone 5. Okay. Construct buildings only in zone 2. Okay, so but that's, you know, that it's not possible. Okay, you need to have buildings even in zone 5, zone 4, zone 3, and zone 2 also. Okay, so you know we are comfortably sitting in this region. Okay, again this is an evolving map. Okay, it keeps changing after every earthquake. Okay, so fortunately much of southern India, okay, is under a safe zone. Okay. So the size of the earthquake and where it happens, how frequently it happens, has helped us in giving one level of understanding about the input parameters for earthquake resistant design. Okay. What the civil engineers are worried about is how the ground shakes. Okay. The ground is going to shake. Okay. When the ground is going to get displaced, okay, rapidly it's going to get displaced. When I say rapidly, it's a relative term. Okay. The ground is going to start moving laterally in both the direction, and there will also be a motion in the vertical direction. There will be 3 components of the earthquake. Okay, you can call it as a longitudinal, along the longitude, along the latitude, the components, and along the axis of the gravity. Okay, there will be 3 components of the earthquake. You need to handle this. Just a typical earthquake record. You can see this is the 1940 El Centro earthquake. Okay, you can see the lateral acceleration was 3 meters per second square, approximately. It's about 1/3 the acceleration due to gravity. Just imagine a building, okay, which is subjected to 1/3 of its gravity loads. Okay, no doubt it's going to experience huge amount of forces. Okay, and the ground displacement also, you can see it's displaced by almost 20 centimeters. It's not a small number, okay, for civil engineers. Okay, the ground displaces. Okay, it's a column moving by 20 centimeters is not a small thing. It's a huge amount of deformation. Okay, our buildings are not so flexible to handle that kind of deformations. Okay, so this is an important input for us. Okay, now with the understanding of the sensitization of what happens during an earthquake and this little bit of science behind earthquakes, we will move to the third and the significant part of today's session, the science behind the seismic design philosophy. Okay, having understood that, okay, the ground is going to shake, it's going to be subjected to accelerations and displacements, okay, and we want an infrastructure to be situated on the surface. How do we move ahead? How do we move ahead is what we are going to learn, and how it is evolved into in a codal provision, okay, how to design earthquakes. For that, now from the crust, the interior of the earth to the surface of the earth, we come to above the surface of the earth to understand structures. Okay, a typical civil engineering infrastructure. Okay, so if you look at any typical civil engineering infrastructure, whether it's a dam or a bridge or a flyover or a water tank or a building or a transmission tower, okay, or a multi-storied building or an educational institution or hospital, anything, okay, you find something which is very, very important. Okay, so if you strip these photographs for all the visual characteristics and try to quantify it in terms of the engineering parameters, every civil engineering structure has got huge amount of mass. It's a huge amount of mass. The amount of mass which we are going to use is unimaginable. If you try to understand what is the mass of this National College, okay, it's unimaginable. Probably you will be able to tell, okay, 1000cc car will weigh about 800 to 1000 kgs. Okay, a two-wheeler may about 125 kgs or 150 kgs. Bicycle 20 kgs. Okay, locomotive 100 tons. Okay, but buildings several thousands of tons. It's a huge amount of mass, and it does not take a lot of understanding to know that when a mass is subjected to inertial forces, okay, that mass multiplied by the inertial force, the acceleration is nothing but the inertial force. So even if the acceleration is small, because of the fact that mass is very large, okay, that's a huge amount of force, unimaginable amount of force. That was the reason why you saw one of the photographs where the flyover had completely tilted. There's a mass which is subjected to inertial force, okay, and it started moving, and the poor spring was not capable of taking that. The columns were not capable of taking that amount of force at all. Okay, so imagine what happens when the water tank starts moving like this. The columns, we don't know how to design. I mean, it's difficult to design those structures for that kind of load. Okay, that's the challenge which civil engineers have. Okay, so all these supporting systems, we call it as the springs of the system or the load-bearing elements, and of course we also have supports or boundary conditions. The ones in a common name, it's called as a foundation to give stability to the structure. Okay, so these are the 5 bulleted points, okay, which are there in every civil engineering structure. You will have mass. Okay, the one which is going to receive the acceleration, okay, converts that acceleration into inertial force. It's a kinetic energy. Okay, and then that kinetic energy has to be transmitted onto the spring. Okay, it will deform, so that will get converted into the strain energy. Okay, you have to design those springs to withstand that amount of strain energy. Okay, of course the springs there are these. It falls under the load transferring components. From the roof it comes to the beam. From beam it comes to the column. From column it goes onto the foundation and things like that. There is a connectivity of elements. While the entire forces are being transmitted from one component to another, you should see that they are all intact. Okay, it's just like if you try to pile cards. Okay, you just blow it, it falls down. Okay, so you need to have a lot of interconnectivity between elements. It's not good enough if each of them behave individually in a proper manner. It should behave well together. Okay, and there is also this energy dissipation mechanisms. Okay, so it does not keep on vibrating for infinite amount of time. Fortunately, structures have got the ability to dissipate energy. Okay, so for the sake of completion, I have included this. I'll just skip this. Okay, so mass, spring, and damping. So at this point of time, we have adequate understanding of this part of engineering. We now have a lot of computational tools to analyze a building, no matter what is the amount of complexity in the building. Okay, we know how to categorize the building, how to understand, how to analyze it for any complex amount of load. Okay, you know you have got 3 components of the earthquake: the X component, Y component, and Z component. So we have got a lot of tools today to understand how the structures are going to behave. Okay, so this is also, it has evolved a lot. Okay, parallelly there is this understanding of materials, how materials behave during earthquakes. Okay, so every material will have a lot of inherent properties. Okay, there are sort of 6 different properties: the strength, the stiffness, energy dissipation mechanism, the deformation capabilities, and so on and so forth. Fortunately, the understanding of materials is also there with us now. Civil engineers have, over a period of several decades, have understood how materials are going to behave. For example, you ask any civil engineer, cast iron, they say it is very strong in taking compression, but very brittle. Okay, and timber, it's very good in compression and tension. Okay, it's lightweight. Okay, but it's hazardous for fire loads. Okay, steel, fantastic material. Masonry is a very vulnerable material to withstand lateral loads. So this amount of understanding is there now. Okay, so over a period of time, okay, civil engineers have spent a lot of time on research and then okay, to understand the material behavior. Now, how are we going to aggregate this or integrate this understanding of material behavior and how the building is going to behave during earthquakes, and then bring in a philosophy to come out with earthquake-resistant design? This is what we need to understand. Okay? So when the mass is going to be subjected to inertial force, it is going to be transmitted onto the spring. It's going to deform. When it deforms, it's going to crush. Whether it is steel or concrete or timber or wood, it's another matter. But there will be some amount of failure. You need to handle this. Okay? You also see one more picture of a devastation. Okay? So broadly, you can put this as a bulleted point. Start with avoiding buildings and infrastructure in seismic. But it's a no. It has happened in many countries. New Zealand for one, okay, Canterbury. So people were displaced. They said no, nothing doing, no buildings in this region. They were all displaced to Christchurch and Wellington and other things. Okay, it's still working there. But you can't say, okay, people in Assam to move to South India. It's not possible. Okay, so that was an approach which is working at some places. The second approach is very interesting. Is the mass which is the culprit. Try to reduce the mass. Use lightweight materials. When you want to use lightweight materials, you can't have multi-stored buildings. It's not possible. And you can't have bridges and dams and things like that. You can't make buildings with lightweight materials. It's a dream for civil engineers to come out with lightweight materials, okay? Which is never going to be achieved at all. Okay? It remains in the dream. Okay? I'm not really sure in the next 100 years or so we'll ever be able to come out with such a lightweight material. Okay? Now, very interestingly, the philosophy is designed something like this. So after each seismic event, people started understanding buildings and earthquake much better and better and better. In a way, it's much like a doctor's profession. Okay? After a disease, they start understanding the disease better. Okay? At the cost of the patient, of course. COVID happened, and then a lot of doctors understood this. Just like that, okay? At the cost of the buildings and then society, we learn a lot. Okay? You need to aggregate all that knowledge, accumulate it, okay? Study the failure pattern, damage pattern, collapse mechanisms, and things like that. Collate and collaborate with different bodies and organizations. Okay, it's a global study. Okay, strategize policies. Okay, we work from whole to part. Understand what are the building typologies and patterns and demography of India. Where is the population? What type of building? Okay, so it has to start from whole to part, and then build capacities. Okay, you need to train engineers and masons and then barbenders and all of them, contractors, okay, all of them to build the capacity to translate that philosophy into technology, into practice. Okay, so the next 2 or 3 slides might be a bit technical, but doesn't matter because otherwise it will not be complete. Okay, so when you take this PPT and then read through this, it's not difficult for you to understand. When you design this typical building, something like this, we design it for a particular load capacity and then add factor of safety and ensure that the deflections and things like that are not beyond certain limits. We are going to impose that. Okay? You don't go beyond certain limits. Okay? That is called as a serviceability limit state. Okay? So this is what we are going to design the normal structures for non-earthquake loads, for all loads except earthquakes. Okay? But during earthquake, okay, very interestingly, it's not a common phenomenon, especially in zone 2 and zone 3 and even for that matter in zone 4 also. Okay? You will allow for certain amount of damages to take place. Okay? For a moderate earthquake, you are going to allow for certain amount of non-structural damage or certain amount of structural damage which you should be able to repair and then reuse it very easily. If there is a major earthquake, you don't want, no matter what, you don't want collapses, which you saw right from 1897 example up to 2001 and probably even now it is continuing. You don't, no matter what, okay? So the design philosophy is like this. The bottom line of the design philosophy is, no matter what, loss of life of people is not allowed. So that's the bottom line. As far as possible, prevent properties from getting damaged. These are the 2 bottom lines for civil engineers. No matter what, buildings should not collapse. No matter what, whether it's a major earthquake or a minor earthquake, whether you are using masonry or timber or bamboo or thatched roof, mud or whatever, whether it is in zone 3 or zone 5 or zone wherever, okay, no matter what, the building should not collapse. As far as possible, the property should not be damaged. Okay, this is the design philosophy, to put it in a very simplistic manner. Okay. Now, given the fact that earthquakes are not such a common phenomena, okay, you don't want to pay a huge amount of premium to protect it from earthquakes. Okay, and you invest a certain amount of premium on the building and design a building in Bangalore, okay, by paying about 30% more premium for earthquakes which are not going to happen. It's not a worthy investment. You're not going to get any returns out of it. Okay, so the design philosophy now becomes a bit more complicated. Okay, so civil engineers have come out with a very, very interesting phenomena. Okay, and in fact, this is a challenge which civil engineers took head on. Okay, what is very interesting is they said, look, no matter what, we'll allow this structure to withstand the earthquake forces. We'll allow the structure to get damaged. We'll ensure that it does not fall down. Okay, so they started working on that. Okay, that's how the technology part is now evolving. Okay, so now if you go to any Western countries, or even for that matter in India, a lot of new modern buildings, they are designed for earthquake forces. God forbid no earthquake should happen. If there is an earthquake, trust me, all these buildings which are designed as per this design philosophy might suffer a little bit of damage. The property may not get destroyed. People will certainly survive. There is no doubt about it. Okay, so this is the crux of earthquake resistant design. Okay, so how to convert that? Okay, now there is a small catch here, and you don't use this philosophy for all the buildings alike. Okay, there are certain buildings like hospitals, and then telecommunication systems, and then very sensitive structures like nuclear power stations, railway buildings, and things like that. Okay, you also need to design it to ensure that the management of such infrastructure becomes easy after an earthquake. You don't want a hospital to lose its functionality after an earthquake. And facilities like dams and nuclear power plants, you should ensure that it should not go into a catastrophic secondary damage and things like that. Okay, so embedded in this design philosophy is also this. Okay, so now the design philosophy is firmed up. Okay, there's enough amount of understanding of behavior and structures during earthquakes. Okay, so to sum it up, it is like this. Okay, so for a non-engineer, okay, you can call it as there is a relationship between the input and output. Okay, input. Okay, what are the factors which you are going to consider? Depends on the location of the structure, whether it is in seismic zone 5 or 3 or 4 or 2. Okay, what type of ground parameters, whether it's an active fault or a passive fault, okay, and things like that. Ground motion parameters are there. Okay, it's a complete topic in itself. Okay, and to what level you want the protection, also very important. These are the input parameters. Okay, output parameters are very interesting. This is very interesting in the sense that the civil engineers are going to control how the buildings is going to respond during an earthquake. Okay, so this is the okay. So how the buildings are going to respond during an earthquake depends on, of course, the importance of the structure. Okay, institutional building more important, residential building less important. Okay, cycle stands and vehicle stands and things like that less important. Okay, because in the event of an earthquake, it may cause damage to the non-people residing components. It depends on the configuration. Okay, you need to ensure the structural integrity. That's very important. So the structural integrity is going to affect the response of the structure. What type of building? Okay, is also very important. Well, load-bearing masonry or timber, steel combination. Okay, things like that. Okay, and how much of energy you will be able to dissipate, and what is the amount of ductility which are. These are the two parameters, okay, engineering parameters. So I'll try to explain that in a very simple manner. Let me see how I'll be able to convey that. Okay. Okay. To sum up, now we know the understanding of ground motions. Okay. We know how to quantify every parameter of the ground motion. What's the maximum duration of the earthquake, frequency content of the earthquake, okay, dominant frequency content, peak values, peak ground displacement, peak ground velocity, peak ground acceleration, everything we know. Okay, and what happens when a building is subjected to this kind of earthquake, we know how. Okay, which point will be subjected to what amount of deformation, what amount of stresses and strains and things like that. There is this. Okay, so over a period of time, several earthquake records were collated. Okay, all over the world, okay? And then we came out with a very interesting design parameter called as a response spectrum. Of course, as I mentioned, one of the few slides which are very technical in nature. I mean, probably even civil engineers find it difficult to understand, okay? So, for the science graduates here, something which is very interesting is, there's a very unique type of graphical representation. It has got 4 scales, one on the x-axis and one on the y-axis, and one at 45 degrees and one at 135 degrees, okay? It's a tripartite graph. We call it as a tripartite graph, okay? Knowing the dynamic properties of the structure, the natural frequency, therefore the natural period, okay? We will be able to know how much of inertial force it will be subjected to, how much of deformation it will be subjected to, okay? In a single plot you will be able to. And embedded in that is the statistics, okay? So, how much it might exceed in the event of a building situated in zone 5, apart from being situated in zone 4 and things like that. That part of the science is also converted into technology now, okay? So now there is this complete firming up of all the things which are very, I would say, formidable for civil engineers, okay? So we have come out with this design response spectra, okay? Lastly, I want to come to the closing part of my thing, okay? Now, knowing the why the earthquake happens, how it has caused damage and then fatalities and things like that, why you need to avoid that, okay? So we have also categorized the sort of type of building, okay? It should be, okay? This is not a wish list, by the way. We want structures to have high strength to weight ratio. We want masses to be lesser. We want structures to have good amount of deformable characteristics, okay? At the same time, we don't want it to be so flexible that during a non-earthquake event, it should not keep swaying like a tree. We can't do that, okay? It should have low degradation, okay? It should not degrade quickly. The connectivity between all the elements should be there, okay? And it should come, this is the bottom line, by the way. Literally, this is the bottom line, okay? It should come at a reasonable cost, okay? You do all the things and comes at the cost of the building itself, nobody is going to practice this, okay? It's just like asking somebody, person who is walking to wear a helmet. I mean, people driving two-wheelers themselves don't wear helmet. Asking somebody to sit in an auditorium or so because you want to protect your head, wear a helmet, it's not going to happen, okay? It's a very complicated policy decision which we need to take, okay? Okay, so the priorities, of course, satisfying all of them is the steel structure, okay? Least one is the inversely proportional. The one which is more damaging comes at a reasonably low cost, masonry structures. The one which is most costly comes at a high cost, okay? So, steel structures, RCC, precast, and things like that. We also have the priority of ordering for earthquake resistance, okay? Now, it does not mean that you should not be doing any masonry structures. It does not mean that you should construct all your buildings in steel. It's not like that. If you are constructing a building in RCC, there is a technological input. There is a way of handling that. How you are going to mobilize ductility and things like that. Okay. So I just thought, okay, if of course when I was teaching this to my students, I used to use a lot of illustrations. I just thought I will share one small thing. You know, this is a very interesting, this is a chalk piece. It can take huge amount of compressive load, okay? But it's very brittle. The moment you apply load, it's going to break into 2 pieces, okay? It's quite strong in compression, okay? Very poor in tension and it cannot withstand any lateral load itself, okay? Now, given this, okay, how are you going to impart earthquake resistant feature into this? Is the challenge which civil engineers faced, okay? So you can see that, in fact, if I drop it, it's going to break into 2 pieces. How civil engineers have come out is very interesting, okay? Now I'm going to apply forces. You can see that it is not broken into 2 pieces. You can actually see this, okay? I can throw this, I can hit it, okay? It does not break into 2 pieces, okay? So we have retained all the essential characteristics of the building if it were not subjected to earthquake. If it is subjected to earthquake, it's going to happen like this. It does not collapse and kill people. Unlike this thing, okay? It's going to break and collapse. So this is the input of civil engineers to this society, okay? Don't think that, okay, a lot of people, there is one way of thinking that a lot of people have died during earthquakes. At the same time, a lot of people have not died because of these things during an earthquake. The way you are going to look at earthquake resistant design and construction is you have to turn it over the other way. Okay? So this is called as the ductility, deformation capabilities, and energy dissipation mechanisms. So this is the one which is imparted. Okay? So, so if it were a masonry building, all you need is a small technological intervention to make this happen. Okay? Okay, so to sum it up, okay, there are 6 virtues in a building: good seismic configuration, adequate lateral stiffness. It should be strong in withstanding lateral forces. It should not be very flexible. Okay, if it were very, very flexible, all buildings will behave like trees. Okay, it should have adequate lateral strength. Okay, it should be ductile. It should dissipate energy, and if it is going to collapse, it should give enough amount of warning to the people, to the inmates, telling that, look, the building is collapsing, please come out, okay? And you can see the building which is going to collapse. So this is how civil engineers have worked out the strategy, okay? I feel this is a very interesting, formidable challenge just taken head on, and then today we have come to a state where we can get all these things, okay? So this is a recap of what, okay? And how are you going to translate all these things? It has come out in the form of monographs, codal provisions, okay? And you see, this is a code book, okay? Earthquake resistant design of structures. And this is a 2016 edition, 2023 edition, 2024 edition has already come out. A lot of people have written books on earthquake, okay? There is this national program on earthquake engineering education. Engineers are trained for this, okay? Sensitized, okay? And there are a lot of professional bodies training this, okay? There is this National Information on Earthquake Engineering, National Information Center for Earthquake Engineering. A lot of people have written books in local languages for people to understand in a pictorial manner, not really in a numerical manner, okay? It's not that you always need to use a software to come out with an earthquake resistant feature, okay? A lot of representations are there, okay? So, and then there is this National Disaster Management Authority, NDMA. We have also come out with some guidelines. Look, if this is the kind of building, this is what you need to do, okay? We are there to help you out, okay? We'll ensure that you are going to follow those things, okay? So this is the broad overview of earthquake resistant design, protection of buildings for earthquakes. I will show you all these things in a small capsule of the next few slides. 2015, there was this earthquake in Nepal, okay? Between the April and 25th April and 12th May, there was a series of earthquakes in Nepal, okay? A lot of buildings, of course, got devastated. And you see the kind of damages, okay? And you see historically important structures, monuments, temples, okay? Fantastic structures, beautiful structures collapsed, okay? It's a general condition of the surroundings in a street, typical densely populated region sitting in seismic zone 5, okay? Okay, this is the kind of thing, okay? And by the way, there is a picture where I saw people wearing masks before the COVID era, okay? So 2015, okay? Something which is very interesting I want to tell with this picture, okay? Earthquakes, unfortunately, they cause a lot of fatalities and damages. It also brings society together. Unknown people help unknown people. One of the natural disasters where unknown people help unknown people without knowing each other. In fact, there are a lot of videos also, and during an earthquake, random people helping each other. Okay, this is something which is very, very important for us to understand. Okay, it happens in any disaster. When, God forbid, if there is an accident, people will come and help you out. Okay, that's something which happens. Okay, so people came. Interestingly, this for our neighboring country, the first people who went to Nepal and started helping Nepalis to come out with this distress is Indians. Okay, from Gujarat, all the people who had experienced all that bad event about 15 years back, they flew to Nepal much before Nepalis themselves could understand how to solve this problem. Okay, so they went there, a lot of people, and you see Rajendra Desai training people, and then they were going to the remotest parts of Nepal and coming out with earthquake resistant technologies and telling them in their own language, look, this is how you need to construct. You are doing this with mud and stone in mud. No, it doesn't matter. Don't change this. We can make your earthquake, make your structure resistant to earthquake. A lot of people came. Okay, so fortunately, I mean, I was also fortunate to be associated through this my former college. Okay, first time I'm telling my former college, rather second time. Okay, so there are of course a lot of questions which are asked. Okay, look, you are telling these things to be done. How are you going to validate? Okay, this is the last part which I'm going to tell. Okay, it's not that everything is done on computers and calculations and then papers and things like that. A lot of laboratory facilities are there. Okay, for instance, okay, this is in Ahmedabad. Okay, a lot of training programs. Okay, so you train people and tell that, look, if you construct your building like this, it is going to withstand an earthquake. If you don't do this, this is what is going to happen. Okay, so this is in business. Yeah. Okay, so with that, I close my lecture. Okay, with these four, you can say takeaways. Earthquake forces are quite complex, and handling them is a challenge. And we now have that complete section of professions to handle them. Okay, so we have that complete understanding. Earthquake resistant design philosophy is based on shared knowledge and evolving science. Okay, so that's another major outcome. Civil engineers play a crucial role. If not civil engineers, who else can do this? Okay, nobody else. I mean, they are responsible for this, and they have been playing a responsible role in this, and this is very important. Okay, God forbid there could be a day when all engineers are IT engineers. Okay, if you don't have earthquake engineers, it's a very dangerous thing. Okay, or if you don't have civil engineers. Okay, practicing earthquake resistant design requires multidisciplinary approach. Okay, a lot of policy matters have to evolve. Okay, so with that, I'm ready to take any questions if there are any. Thank you. ಇದು ಶೇರ್ ಮಾಡ್ತೀರಲ್ವ ಇದು? Last 2 men in the musical chair.
Good evening, everyone. You want to ask anything, any questions regarding this session? Students who are sitting in the back side, ಏನಾದರೂ ಪ್ರಶ್ನೆ ಕೇಳೋಕ್ಕಿದೆಯಾ? No. So how was the session today? Was it interesting? Yes, to know about the artwork and all. Of course, it is interesting. So, on behalf of National Education Society of Karnataka, I would like to thank Dr. S. Raghunath sir for lending his valuable time with us. Thank you everyone for taking the time to be here today and listening Dr. S. Raghunath sir seminar. And the topic was so interesting and knowledgeable for all of us being a science student, and it is also important for us to know what is an earthquake and even the science behind it as well as the technology. So thank you, sir, for sharing your knowledge with us, and I would like to express the appreciation to all of my friends and our principal, vice principal, and Sucharita ma'am. Thank you.